You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Operating system vulnerabilities are weaknesses within the core software that manages hardware and fundamental system functions. Unlike application vulnerabilities, which exist in business-specific logic, OS flaws affect the underlying platform that all applications depend on. This makes them particularly dangerous, as a compromise can provide attackers control over the entire system. Examples include kernel flaws, privilege mismanagement, and poorly secured system services. Because every process and user relies on the OS, attackers see it as a high-value target. Defenders must approach OS security with the understanding that if the foundation is compromised, all layers above it are equally exposed. Common sources of OS vulnerabilities include unpatched kernels, misconfigurations, and flawed drivers. Kernel vulnerabilities allow attackers to interact directly with the system's core, often leading to complete control. Misconfigurations, such as overly permissive file permissions or unnecessary services left enabled, expose avoidable risks. Device drivers, which connect hardware to the OS, are another source of vulnerabilities if poorly written or outdated. Attackers exploit these flaws because they exist at a low level, where security tools may have limited visibility. For defenders, recognizing these sources emphasizes why OS security is not static. It requires ongoing maintenance and vigilance. Privilege escalation vulnerabilities are particularly concerning in operating systems. They occur when flaws allow attackers to elevate their privileges beyond what was originally granted. For example, an attacker with basic user rights might exploit a bug to gain administrator or root access. Once elevated, the attacker can disable defenses, install malware, or exfiltrate data without restrictions. Privilege escalation turns a limited compromise into a catastrophic one, which is why these vulnerabilities are prized by attackers. Defending against them requires a mix of patching, proper permission assignments, and monitoring for unusual privilege usage. It highlights the stakes of OS-level weaknesses. Patch management for operating system components is one of the most critical security practices. Once vulnerabilities are discovered, vendors release updates to close them. If patches are not applied promptly, attackers can exploit widely known flaws, often using automated tools. OS patches cover not only the kernel, but also services, utilities, and drivers. Effective patch management requires a balance, applying updates quickly while ensuring they do not disrupt stability. Organizations that fail at this often become victims of attacks, exploiting vulnerabilities that were already fixed. Maintaining disciplined patch cycles transforms OS security from reactive firefighting into proactive risk reduction. Web-based vulnerabilities differ from OS flaws in that they exist in services exposed through web servers, applications, and supporting infrastructure. These weaknesses are particularly dangerous because web servers are often directly accessible from the Internet, making them the most visible part of an organization's attack surface. Vulnerabilities may involve misconfigured web services, insecure application code, or improper permissions on web directories. Attackers target them because they provide both visibility and access to sensitive back-end systems. Defenders must treat web-based vulnerabilities with urgency, as exploitation often happens rapidly once exposure is identified by automated scanners. Web server misconfigurations are among the most common and preventable web-based vulnerabilities. Examples include leaving directory listings enabled, which allows attackers to browse server contents, or retaining default pages that reveal software versions. Misconfigured error handling may inadvertently expose sensitive information, such as system paths. These issues are not advanced exploits. They are lapses in administration that create unnecessary openings. Attackers often start by probing for these weaknesses, as they require little effort to exploit. For defenders, disabling directory listings, removing defaults, and minimizing information leakage are foundational practices that prevent trivial but damaging compromises. Server-side weaknesses often involve insecure file permissions and violations of the principle of least privilege. For instance, a web server process running with full administrative rights increases the damage potential if compromised. Similarly, files containing sensitive configuration data should never be globally accessible. Attackers exploit these oversights to escalate privileges or pivot deeper into the system. Properly applied file permissions and privilege separation ensure that even if a service is compromised, its reach is limited. This approach reduces the attack surface significantly, preventing single flaws from resulting in full system compromise. Least privilege remains as vital at the server layer as in user accounts. Weak session management in web applications can also impact oxygen monosulfide level security. If attackers hijack user sessions, they may gain unauthorized access to applications running on the server. From there, they can attempt to escalate privileges or exploit underlying OS vulnerabilities. Poorly protected cookies, long-lived sessions, and predictable tokens all widen this attack surface. Weak session practices thus act as a bridge between web-based weaknesses and deeper system compromise. Defenders must recognize that web layer security is inseparable from oxygen monosulfide layer integrity. A compromise at the web application level can cascade into full system exposure if session controls are weak. Improper input handling at the web layer is another path to OS exploitation. Web servers that fail to sanitize inputs may pass harmful commands directly to the operating system. Command injection attacks illustrate this risk, where attackers manipulate inputs to run arbitrary system commands. For example, a poorly secured file upload feature could allow an attacker to execute scripts directly on the server. These attacks blur the boundary between application vulnerabilities and OS vulnerabilities, as the application becomes the vehicle for exploiting underlying system functions. Input validation and output encoding must therefore extend across both layers for effective protection. Secure default configurations are essential for both operating systems and web servers. Out-of-the-box settings often prioritize ease of use, leaving unnecessary services enabled or default accounts active. Attackers are well aware of these defaults and actively search for them. Organizations that fail to harden systems before deployment effectively invite compromise. Secure baselines must disable unnecessary services, enforce strong authentication, and limit exposed functionality. Whether at the OS or web server level, default configurations must never be left untouched in production. Hardened defaults represent the minimum standard for reducing predictable and avoidable vulnerabilities in critical systems. Logging and monitoring provide defenders with visibility into both OS and web layer anomalies. For operating systems, this includes tracking login attempts, privilege escalations, and unusual process activity. For web servers, logs capture access patterns, request anomalies, and potential injection attempts. Monitoring transforms raw log data into actionable intelligence by flagging behaviors that deviate from normal baselines. Without it, attackers can operate undetected for long periods. With it, defenders gain early warnings that allow them to intervene before damage escalates. Effective logging and monitoring bridge the gap between prevention and detection, ensuring vulnerabilities are not silently exploited. The combined threat of OS and web vulnerabilities creates a broad and dangerous attack surface. While each type of flaw can be damaging on its own, together they form pathways that attackers can chain into devastating compromises. For instance, a misconfigured web server may expose credentials that allow exploitation of an unpatched OS vulnerability, or a kernel flaw may be leveraged after gaining initial access through weak web authentication. Defenders must recognize that OS and web vulnerabilities are intertwined, demanding integrated protection. Treating them separately risks overlooking how attackers combine exposures into powerful, layered attack strategies. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Hardening practices for operating systems begin with minimizing the number of services installed and running. Each unnecessary service adds to the attack surface, offering potential entry points for attackers. A hardened system runs only the essential components required for its intended role. Regular patch cadence is equally important, ensuring that vulnerabilities are addressed quickly before they can be exploited. Combined, service minimization and disciplined patching reduce exposure significantly. Hardening also involves removing unused accounts, enforcing strong password policies, and disabling insecure defaults. By treating the operating system as critical infrastructure rather than a generic platform, defenders prevent it from becoming the weakest link. Secure configuration of web servers is just as vital. Administrators should disable directory listings, remove default content, and configure error messages to reveal minimal information. Security headers like Content Security Policy, X-Content Type Options, and Strict Transport Security help enforce safer client interactions and prevent attacks such as cross-site scripting. Web servers should be configured to use strong encryption for all communication, eliminating outdated protocols like SSL and weak ciphers. Regular audits of configurations ensure drift does not reintroduce vulnerabilities. Insecure web server setups remain one of the most common attack vectors because they are visible to anyone online, making secure configuration a non-negotiable practice. Role-based access controls, RBAC, and carefully managed file permissions are fundamental to operating system security. RBAC ensures that users are assigned only the privileges necessary to complete their work, reducing the impact of compromised accounts. File permissions enforce boundaries, preventing unauthorized users or processes from altering critical files. A compromised user account with limited access poses far less risk than one with administrative rights. This principle extends to services as well. Web servers should not run with root or administrator privileges. By enforcing strict RBAC and permissions, defenders contain damage and ensure attacks cannot escalate unchecked through the system. Application isolation techniques reduce the impact of web-based compromises on the underlying operating system. Methods such as root jails, containers, or virtual machines restrict applications to controlled environments. If an attacker compromises the web application, isolation ensures they cannot easily affect the host system or other applications. Containers provide lightweight, consistent environments, while virtual machines offer stronger separation at the cost of performance. These tools reflect a defense in-depth strategy, where breaches are contained and segmented. Application isolation recognizes the reality that not every vulnerability can be prevented, but damage can always be limited with careful design. Web application firewalls, WAFs, add an important layer of defense by filtering and monitoring traffic between clients and web applications. A WAF can block common attack patterns, such as SQL injection or cross-site scripting attempts, before they reach the application. Unlike network firewalls, which focus on ports and protocols, WAFs understand application layer traffic and enforce security policies accordingly. They are not a substitute for secure coding, but serve as a valuable shield against automated attacks and opportunistic probes. By reducing the number of successful exploit attempts, WAFs help organizations buy time to patch underlying vulnerabilities without leaving systems exposed. Timely updates for kernels and drivers are essential to reduce the risk of operating system compromise. Attackers often exploit outdated drivers to gain low-level access, bypassing higher-level defenses. Regular patching ensures known flaws are addressed, but updates must be balanced with stability testing to avoid disruptions. Organizations sometimes delay kernel updates for fear of outages, but this hesitation leaves systems exposed. A disciplined update cycle, combined with rollback plans, mitigates this challenge. By staying current with both OS kernels and hardware drivers, defenders close vulnerabilities that could otherwise provide attackers with privileged and persistent access to critical systems. Integrity monitoring of critical OS files and binaries provides defenders with early detection of tampering. Tools can calculate cryptographic hashes of key system files and alert administrators if changes occur unexpectedly. Since attackers often modify binaries or configuration files to establish persistence, Detecting these changes quickly is vital. Integrity monitoring does not prevent attacks, but it reduces the time attackers can remain undetected. When combined with logging and behavioral monitoring, it creates a layered detection system. Integrity verification helps ensure that the foundation of the operating system remains trustworthy, a prerequisite for all higher-level security functions. Secure deployment practices are equally important for web content. Applications should be deployed from signed packages to verify authenticity, and all dependencies should be vetted for vulnerabilities. Unsigned or unverified packages leave room for supply chain attacks, where compromised components are introduced during the deployment process. Defenders must ensure that pipelines enforce code signing and dependency checks automatically, reducing reliance on manual oversight. By treating deployment as part of the security lifecycle rather than a final step, organizations prevent compromised content from entering production environments. Secure deployment transforms the web layer from a liability into a resilient, managed asset. Runtime monitoring provides visibility into both operating system processes and web request patterns. For the OS, this means tracking processes, memory usage, and system calls to detect anomalies. For web servers, it involves monitoring request volumes, error rates, and suspicious query strings. Together, these signals reveal when systems are under attack or behaving abnormally. Runtime monitoring is proactive, catching issues in real time rather than relying solely on after-the-fact log reviews. By continuously observing behavior, defenders can intervene quickly, stopping attacks before they escalate. Visibility at runtime ensures systems are not only configured securely but also actively watched for compromise. Rollback and recovery plans are essential when OS or web layer updates fail. While patching is critical, not every update integrates smoothly with existing environments. If an update causes instability, defenders need a tested procedure to revert to a known good state quickly. Backup images, redundant systems, and staged rollouts all support this recovery. Without rollback plans, organizations face a dangerous choice between running unpatched systems or risking downtime. Attackers exploit delays created by failed updates, knowing defenders may hesitate to apply fixes. Recovery planning ensures organizations can patch confidently, secure in the knowledge that stability can be restored if needed. Configuration management and automation prevent drift, which is a major contributor to vulnerabilities. Over time, systems naturally diverge from their intended secure state, as administrators make ad hoc changes. Configuration management tools enforce consistency by automatically applying secure baselines and flagging deviations. Automation ensures changes are tracked, reproducible, and reversible. This prevents insecure settings from creeping back into environments unnoticed. Without these tools, even well-hardened systems degrade over time, expanding the attack surface. By integrating configuration management into daily operations, defenders create a sustainable cycle of secure deployment, monitoring, and correction across both OS and web layers. Ultimately, defenses for operating systems and web servers must be layered and complementary. No single control can eliminate all risks. Instead, minimizing services, enforcing strict permissions, patching diligently, isolating applications, and monitoring continuously create a resilient environment. Web servers are hardened with proper configurations, security headers, WAFs, and signed content. OS layers are secured with RBAC, integrity monitoring, and disciplined patch cycles. Together, these defenses ensure that vulnerabilities are harder to exploit and easier to detect. The integration of technical, operational, and procedural safeguards creates a strong defensive fabric against attackers targeting the foundation of IT environments. In summary, operating system and web layer vulnerabilities represent some of the most exploited weaknesses in cybersecurity. Attackers target them because they are visible, foundational, and often neglected. Defenders must respond with structured hardening, proactive monitoring, and layered defenses that span both domains. By treating OS and web vulnerabilities as interconnected, organizations avoid gaps that attackers might chain into devastating compromises. Security is not about perfection, but about making attacks difficult, noisy, and unrewarding. With disciplined hardening, continuous monitoring, and recovery readiness, organizations significantly reduce their risk from these critical, ever-present threats. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.